Okay, Tuesday, May 5th. Okay, all right. So it is the beginning of 7:45 a.m. on Tuesday, May 5th. So I would like to start with this warm up. It's a good review of the things we were talking about. I would like to use the presentation method, let's say, that reduces the number of errors that could be written down. It's nice. It kind of compartmentalizes things. I would suggest doing it in this way of taking the original question and just looking at the indefinite integral. So the integral without the x equals 4 or x equals 5 listed. And we'll just look at this indefinite integral problem. Now, some indefinite integral, so you're always finding an antiderivative when you're talking about an indefinite integral, but some of the times you just need to use a pre-substitution method. Sometimes you need to do some algebra first. In this case, we do need to substitute. The substitution that's going to work here is going to be u is equal to x squared plus 1. So du over dx equals 2x, and then solving for dx, we'll have du over 2x is equal to dx. So we'll go back to this indefinite integral that was here. I just kind of had to write that down once to see what we should do. And now let's substitute some things. So the x squared plus 1 down there is replaced with u, and dx here is replaced with this fraction du over 2x. Please be careful here. I think a thing that sometimes happens, I saw a thing like this actually occur, at least on some rare occasion in the exam, is 6x over 2x. Sometimes people will turn a thing like that into 4x. Oh, by the way, exam, it's posted. Please also look at the key. Look at the key. Um, every time something's graded, the key is available, so please take a look. So sometimes what happens is people take 6x over 2x and turn that into 4x. Well, 6x minus 2x would be 4x. Here instead you got to cancel the x on top and bottom. The 6 over 3 would cancel to give you a 6 over 2, excuse me, would cancel to give you a 3. That after all those cancellations here, the u is still in the denominator, so don't let that just kind of move automatically into the numerator. And then now we're at a stage where we're ready to take this thingy and anti-differentiate. So this should be 3 times ln of absolute value of u plus c, and then replace the u with what we selected a moment ago, which was x squared plus 1. Okay, so there's the indefinite integral, right? So we were given a definite integral, but for a moment we looked at the indefinite integral, did some substitution work, and finally got down to this 3 ln of absolute value of x squared plus 1, closed absolute value plus c. Then we can go back to the definite integral that was asked in the warm-up, and now we just take this portion right there. I want to use the most convenient antiderivative, so it's the one where you use c equals 0. And then plug in x is 5 first, and then plug in x is 4 next. Be sure it's that order. Sometimes people swap the order. So we'll have 3 times ln of absolute value of 5 squared plus 1 minus 3 times ln of absolute value of 4 squared plus 1. Um, if so, this is the preferred method, really. You have a definite integral, just write the indefinite integral first and work on that problem, especially if you have a substitution, because the big deal yesterday was to talk about how you've got to be very careful if you're going to do substitution together with a definite integral. So if, for instance, I never did it using the approach I have here, but if you did write a definite integral which has a du in it, or ends in a du, then the endpoints of integration must be 17 and 26. So this would be correct, right? Integral. So people would write sort of a version of this integral 3 over u du and accidentally still have the 4 and 5 in these two spots, but it would need to be a 17 and a 26, so put a happy face there. Incorrect things that people would do, I mean, not that I've given this specific problem, but if I mimic the error that people make, they'll write integral 4 to 5 3 over u du. And I also actually here, sorry about this, meant to have the same 4 over 5, so I'll update that when I repost the slides. So yeah, again, I think the thing to do with a definite integral, if you're not going to do this using the area method, it's write down the indefinite integral. It just leads to fewer errors. Okay, today is a Tuesday, so please do the online quiz that's available today. There will be one final one on Thursday. I would suggest you start WebWork 43 today. Because the final due date for the assignment is on the Monday of finals week, though, I did decide to make WebWork 43 extra credit. So I guess in principle you could not do it. I would just start it today so that you don't have to worry about it next Monday. Office hours that remain for the rest of the semester are posted. If these times don't work, please set up an appointment. And the final exam will be made available on May 12th and should be turned in by the end of the day on May 13th. You have to pick your own 6-hour window of time to work on it. Okay, today I think... Am I muted? Let me check on a thing here. Hello? Okay, so I tried unmuting. Sorry, I didn't change anything about my microphone setup, but on the second machine where I'm logged in as a student is logged in, I just undid the speakers and I heard myself. So, so, the the audio I believe is working. I've got somebody else signed in who might be able to confirm one way or another. The audio is on. Yeah, so I mean, yeah, so you may need to check your speaker settings or sign out and in. Well, okay, I'm gonna... All right, thanks for the... Okay, I'll leave up this next thing here. Okay, gotcha back. Let's see. Do we have sound? Hello? Check. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3. 1, 2, 3. ABC. You might try the dial-in phone number if I don't have a confirmation one way or another. I'm gonna talk my way through this and then I'll see what happens here. Um, yeah, maybe I should type that in case I don't know the phone number off the top of my head, but there Canvas also lists a dial-in option using a phone. All right, so I gotta kind of keep moving if I don't know what the status is. All right, so okay, so the setup today actually is kind of rather nice. I think we looked at kind of more tedious things yesterday, to be really honest. Um, in this question, there are two functions, x squared plus one. So think about that, right? This x squared plus one. Oh, geez, let's see. Let me like this x squared plus one thingy, right? So that should be like, well, this should be the parabola that just shifted up one unit, right? So then, and then this other function is y equals x over 2. So x over 2, that's the same as 1 half x. I mean, this is actually a y equals mx plus b. The slope is 1 half, so it's really shallow, right? It's a line. If the y-intercept is 0, it goes right through the origin. So you got these two things, and then what's the area between the two graphs from x equals 6 to x equals 10? So we're looking at a region, and I actually have a much nicer copy of this here. So here's the graph of f, right? There's the graph of g. So g is a very shallow line, and we're asking what's the area between these two. So I've shaded this area in between in yellow. So we only want the region in yellow to answer this question. Unfortunately, the area that we want is in yellow, but if we set up the integral of f from 6 to 10, it would represent both the yellow and the blue regions. But we only want the yellow region right now. We don't want the yellow and the blue region, so why don't we subtract away the blue area, right? So the blue region, since this is g, the blue region is found by doing the integral from 6 to 10 of g. So the yellow region, which is what was asked, we wanted the yellow region, the yellow region would be the integral from 6 to 10 of f of x dx minus the integral from 6 to 10 of g of x dx. Another way to write that, you can write this as two separate integrals like this, that's fine, but you can also compact this using one of the rules for definite integrals and have the integral from 6 to 10 of f minus g dx. Right? So this integral right here represents this shaded region in yellow. And that's, I mean, the whole point here is the integral of f alone gave you too much stuff. It gave you the yellow and the blue. So we just needed to get rid of the part in blue, which is its own integral. It's just the integral of g from 6 to 10. And this, I mean, this one idea, we just kind of run with this. And let's, before we dig into it too much, let's just put this all into a box, right? So what really happened here is if f of x is greater than or equal to g of x for all x inside an interval from a to b, then the area between the graphs of f and g and between the vertical lines x equals a and x equals b is given by this here. It's what we had just set up. Take the two functions, subtract them from each other, integrate that from x equals a to x equals b. By the way, this first part here, f greater than g, excuse me, that just in the picture just means that if you graph f and you graph g, then f is above, right? By the way, if f of x is greater than or equal to g of x, then when you do f minus g, that should always be bigger than or equal to 0. And if what you're integrating is bigger than or equal to 0 for all x values, then it turns out that the value of capital A is going to be greater than or equal to 0. Um, like I yeah I sorry I gotta run like you you gotta take that phone number and then type in an the 9-digit access code. So um, the other thing you can do is if you dial my office phone number, it'll ring my phone, and I'll leave that on in speakerphone mode. But that's trying to do what I can right on the fly. But you know, there's okay. Um, okay. Uh, so here's the thing: to contrast this new integral that we're setting up here compared to the definite integral we talked about before, the integral from a to b of just a single function f of x, right? So this was a signed area. This formula up here is always going to give you a positive area. Seems a little strange, but the argument here was if f is greater than or equal to g, then f minus g is always bigger than or equal to 0, right? So this will always give you the actual, so the space between two functions. It'll give you that area in a positive sense, um, versus the integral of a single function that'll give you a signed area. Okay, so let's take a look at an example. Right? So what is the area between y equals 1 half x and y equals 3 to the x plus 4 from x equals 2 to x equals 6? So for all of these, you got to do a bit of a small graph. It doesn't have to be a very, not a 100% accurate graph, but you've got to take a go at this. Like if you graph y equals 1 half x, that should be a line, right? It was a line that we actually talked about in the previous example, a slope 1 half. And then you have this, y equals 3 to the x is an exponential function. You just shift that up 4 units. And I have a picture of this that I'd like to show. Okay, so we've got the red line here. It's rather shallow here just because of how tall the picture is. And you've got y equals 3 to the x here in blue. The region that we're trying to get is this area here. Right, so this purple region, notice it's missing this part down here. This is, so the blue curve is above, right? This exponential curve shoots up really huge in comparison. Right, so there's that link if you want to look at it later. So even with a very quick sketch, the whole point is that this one is above that one, right? And so then the area, so the area here to set this up, it should be the function that's above minus the function that's below, setting up an integral from x equals 2 to x equals 6. Okay, so this definite integral that we set up represents that purple area, right? It'll end up being positive, and it represents that total area. Um, to find this area, if we wanted to find this area, I would say let's look at the indefinite integral. And so leaving off the 2 and the 6 for a moment, and when you integrate, you have this 3 to the x over ln3, 4 anti-differentiates to 4x, copied the 1 half, anti-differentiate the x, and you have an x squared over 2, and this plus c. And then you can take this antiderivative right here and plug in 6 first, and then plug in 2 next, right? And then you'll have that this integral turns into, so took this antiderivative portion here, plugged in x as 6 first, then plugged in x as 2 next. Okay, how are we doing with that so far? And I see a phone sign in, so maybe do you want to type that we're doing okay so far? Sorry about I have no idea what, Okay, yeah. And you may notice that what you see from being signed in and uh, what you hear might be not in sync with each other a little bit, right? Okay, so let's see. So here, this number represents the area. It will be positive. It represents that area that's shaded in purple. And here's the thing. Today, we'll focus less on computing the integrals. Okay, so all of the integrals that are given, we're just going to set up an integral and say, yesterday we would have talked about solving it all the way through. Today, the idea is we have a question, want to draw a rough. Oh, whoops. Let's see. Okay. Well, today the idea is we have a question up at the top. We're given some functions. We're given vertical lines. We want to sketch it at minimum in our minds, and it doesn't have to be a perfect sketch, but we've got to know which one's above and which one's below, because the one that's above we put before the minus sign, the one that's below we put after the minus sign. And we want to like, based on a relatively accurate picture, set up an integral. And we will not finish the integrals all the way through. So this is the last integral that we're going to completely finish today, right? Like today the goal is to get to set up the integral. So let's take a look at this one. Right? So um, what is the area between y equals negative x minus 4 and y equals x squared plus 3 and x equals 10 and x equals negative 1? So first of all, x equals a number, x equals a number. Those are two vertical lines. Um, uh, y equals negative x minus 4, that's a line, right? This is a y equals mx plus b. M is negative 1, b is negative 4. Over here you have y equals x squared, which would be sort of our usual parabola, and then plus 3, meaning you shift this up 3 units. So just in terms of a sketch, we should be picturing a line whose slope is negative. I mean, even in a rough sketch, okay, negative 4 is the y-intercept and slope is negative 1. It looks roughly like that. Versus this parabola, y equals x squared plus 3, so 3 units up, and you have a parabola that's like this. Now, if you draw this too sharply, it'll be hard to draw in that, because this keeps going no matter what. Like sometimes we draw this a little too much like this or whatever, but it does keep going, and at some point there's 10, x equals 10, and it does cut through the parabola eventually. It also cuts through this line eventually, and then x equals negative 1, maybe it's like right here. And so then we have this shaded region that we're trying to find. I do have, again, that's a very rough sketch, and that's the kind of thing, like a 5-second sketch of the types of functions that appear here is expected. I have already clicked on a link. I'll pull this up here. That what we have is, oh, come on, processor speed here. Okay. Well, hang on. Just give it a moment to load here. So we've got this blue parabola. We have this red line. The red line slope should be negative 1. It doesn't look quite like that just because I had to shrink the y-axis a bit so that we could see what's going on here. But the region we're talking about here is shaded in purple. Okay, so you can click on that link if you'd like to explore a little later. So look, even from a rough sketch, you would see that the parabola, like even without the graphing calculator, you would see that this x squared plus 3 is the function that's above. And so we do that upper function minus lower function, and we integrate this from negative 1 to positive 10. Okay. The one thing I'll state about this one is notice that parentheses around, like here the parentheses around x squared plus 3 that's not really required. It's nice visually to have them there, but here the parentheses are required. Why are the parentheses required? Right, the parentheses are required because there's two terms here, and it's two terms after a minus sign. Yeah, order of operations business, right? So we have to, yeah, and I included that reasoning here. Yeah, there's more than one term. It's behind a minus sign. It's an order of operations issue. Okay, so that's the game here. Just like a rough sketch, enough. It doesn't have to be totally accurate, but just enough to like figure out which function's above and which function's below, right? So I have two examples I'd like you to set up the integrals for. So the first one is set up an integral for the area that's between y equals e to the x. That's an exponential function, right? And y equals negative x. And the vertical line's x equals 3 and x equals 4. And then the second one is to set up an integral which represents the area between y equals 5 minus x squared and y equals x squared minus 13. And the vertical line's x equals negative 2 and x equals 1. So I want to just give you a moment to get your feet wet and try this. We'll do the. I'll have a full thing on this slide in a moment. Okay, so for the first one, you have this exponential function. Um, Sometimes it's helpful to draw axes for these. Sometimes it's not actually, right? Like for this one, I think it's. I'll draw in some axes, and you've got this exponential function that looks, something like that with this y-intercept of 1. You have this line y equals negative x, so that's a line, right, that goes through the origin of slope negative 1. And then you have these vertical lines, x equals 3, x equals 4. They're all right next to each other, actually, right? Vertical line there, vertical line there. And really the only, the question, the region that's being asked about in this first question is actually that sliver of space. And yeah, sure, over back here, there's this crossing, and then the line is above the exponential. But in the part that we care about over here, the exponential is above the line. Right? So I try to put at least some words to this here. So the exponential curve is in the first and second quadrants, And at least for x values between 3 and 4, the graph of y equals negative x is only in the fourth quadrant. Right? So here's a link to a picture. Let me just pull this up for a moment. Again, this looks a bit skewed only because the x-axis doesn't have much. The x-axis here just goes from like -1 to +10, but this exponential curve, right, the blue curve, y equals e to the x, is exponential. I had to like make the y-axis go from like -10 to +70 just so that we could see what's going on. And so that's why this line, even this red line, even though the slope is -1, it doesn't quite look like it looks a little shallower than that, just because of the scaling. So it's that region here in purple that is meant to be the same one that if I just step back in the slides just for a moment, that's meant to be the same picture. So then to set up an integral, the one that's above is the exponential. The one that's below is the negative x, and I just stuck this in. I maybe didn't have to put this one in parentheses, but I thought just because there's a minus and a minus, it's just helpful to use a set of parentheses for the visual effect. And again, let's just clear up that the original function here was a minus x. That's why there's this minus sign. And then the formula here for the area between two curves has a minus sign. So that's why there's a second minus sign. Of course, if you want, you could rewrite this as integral 3 to 4 e to the x. The minus minus can become plus x dx, and so on. Again, today's goal isn't about finishing off these integrals. In fact, the integrals we're looking at today aren't all that bad. They don't usually even require substitution. Today's about like let's think about what graphs look like and then set up integrals. So I hope that one's okay. The second one, well, I'll just pause for a moment, see if we're doing okay, see if a question comes up. Okay, the second one though, let's see, y equals 5 minus x squared. Well, so there's that x squared business. We should see a parabola of some kind, right? Now, due to the fact that the coefficient on the x squared is negative, this should be an upside down parabola. Versus right here, y equals x squared minus 13, because the number in front of x squared is a plus 1. That should be the sort of the right side up parabola. And then x equals a number. Those are vertical lines, not horizontal lines. Right, so we've got an upside down parabola that's been shifted upside down. I'm trying to say that. I mean, if there was sort of an original parabola. So we've got an upside down parabola that's shifted up 5 units. And then you have this regular kind of parabola, y equals x squared, that's shifted down 13 units. And then you have these two vertical lines. So let me bring up this picture over here. I already clicked on the link. So you see here the upside down parabola in red, kind of a right side up parabola that's been shifted down 13 units. You can see down here, in fact, I didn't click on it, but you'll see, yeah, the vertex of the parabola is down at y equals negative 13. And the region that we were asked about, the question said for x between -2 and +1. So that's this purple region here. Okay. One thing to notice is that the red curve is above the blue curve in this purple region, right? Now, other times the blue curve is above the red curve. In fact, you'll notice that there's this intersection here. This is one of the places the two parabolas intersect. The point 3 comma -4. Here's another place where the two parabolas intersect. The point -3 comma -4. So if the picture is not accurate enough, we need to be careful of these kinds of things. So you'll notice that x equals 1 and x equals -2, those are the provided x values in the problem, that they are in between x equals -3 and x equals 3. Right? We were provided x equals 1 and x equals -2. These two vertical lines are in between. It's not like this line. Let me just change it just for a moment. It was x equals 1. That was just given in the problem. It's not like that was over here somewhere, right? That would have been a problem. So we should, I think, to do this question thoroughly. I mean, we are using a graphing tool right now, but I'm just trying to warm you up to this idea that we should probably think about how an upside down parabola and a right side up parabola just themselves are going to intersect in two locations, right? That's how a concave down and a concave up shape are going to intersect. And we should work on finding those intersections. So anyway, at least from the picture for this one, and I'm warming up you up to a bigger idea in a moment, we have the upside down parabola is the one that was above. We have the right side up parabola that was shifted down 13 units. That's the function that's below. And even that, just the idea that this one's above and that one's below, I I want you to picture that, almost without even graphing, right? Because upside down parabola, and then you shift that up 5 units. That should be the one that's above. Okay, so we have the upper function minus the lower function, and then we stick the smaller x value here, negative 2 to positive 1. But I think the big question that would come up in this, and I tried to demonstrate this in the picture to get your feet wet with this, is these two parabolas intersected, right? How could we come up with the intersection? And we saw in the picture that the intersections occurred when x equals 3 and x equals negative 3. We could have determined that actually using algebra, even without, like with the graph. It's hard to make the graph accurate enough without a tool to see this. But you can how could you get this? What you'd have to do is you'd set the y's equal. So set the 5 minus x squared, which is y, equal to x squared minus 13, which was the other y. And setting those equal and solving would get you those x values. We'll see a version of that in just a moment in another question. In fact, take a look at what's strange about this question. So let me read the question off here. So we've got find the area enclosed between y equals x squared minus 2 and y equals x plus 4. So notice that in this, if we just inventory, we were given a parabola and a line, right? So we've got this parabola, kind of the standard y equals x squared parabola, shifted down 2 units. We have y equals an mx plus b, so with an m being 1 and the b being 4. So we have a parabola and a line. The parabola is concave up, right? So, I mean, I know I've phrased this kind of using more algebra terminology so far. If the coefficient in front of x squared is a positive 1, therefore that should be the kind of usual direction parabola and not upside down. But I'm trying to just provide a reminder that another approach to seeing which direction the parabola goes, you could take the second derivative. And you could almost take the second derivative without writing anything, right? So if you had your function x squared minus 2, you take the first derivative, you have 2x, and you take a second derivative, you have 2. Since that second derivative is a positive number, this thing's concave up the whole time. Doesn't even depend on what x is. So you have a concave up parabola, and you have a line. How are they going to intersect? Right? So if they intersect at all, if you've got a parabola that's concave up and a line, in the region that's enclosed between, the line is above. So in this shaded region, if you start anywhere in the shaded region, if you walk upwards, you'll hit the line. Whereas if you start in the shaded region, let me kind of erase a little bit in here. If you start in this shaded region here and then you walk downward, you end up hitting the parabola. Right? So the line is above, the parabola is below. Okay, here's the other thing. In the question, we were not given x values at all. We're just, there's a parabola, there's a line. We want that entire shaded region. We weren't given x values. So what should, we already see this, that the line was above, the parabola was below. So there's the x plus 4 part minus the parabola, x squared minus 2. But what should a and b be? How should we figure out what a and b are? Well, we should see where the parabola and the line intersect. So what we should do is set, if we're going to see where the parabola and the line intersect, we should set these y's equal to each other. Right? One of the y's is x squared minus 2, the other y is x plus 4. If y is y, we should set those equal. So I set equal here, x squared minus 2 equals x plus 4. And if we solve this equation, we'll see where the parabola and the line intersect. So we'll solve this is a quadratic equation, right? The highest power of x is a 2. So in the end, we'll try to factor, and if factoring doesn't work, there's always the quadratic formula. So I wanted a 0 on one side, so I subtracted x on both sides. I subtracted 4 on both sides. I believe this will factor as x minus 3 times x plus 2 equals 0. And so then, sorry for the spacing, this should have appeared on its own line, but you'll have here then, you can set each factor equal to 0, so x minus 3 equals 0, x plus 2 equals 0, and when you solve each of those little equations, you have x equals 3, x equals negative 2. So so now we actually have an answer to this question over here. What should a and b be? The a is the smaller x value of negative 2, so that's down here. The bigger x value of 3 is written right there. Okay, that's setting up the integral. And I wanted to demo this one without having drawn a picture yet. Are we doing okay kind of overall with this? I do have a picture to show you, but I just wanted to say like we really went through the thought process without having used the graphing tool to see the picture. But I have that. So let's demo that. So what I have on the other window that I'll slide over here is I have the y equals x squared minus 2. I have y equals x plus 4. I shaded the region that we need in blue. And then I picked two random x values called a and b. Now, of course, we know from having solved the equation that the two correct x values we need for the integral are negative 2 and positive 3. But let's just say we didn't know yet. Like, let's just go back to like up here when we were like, we weren't given x values. What should those x values be? And we're at that stage, and so kind of pretend we don't know this information about x equaling 2 or negative 3 yet, right? So just if we were to explore, maybe it looks something like this, right? So there's the line which is above, the parabola which is below for this region in blue, right? The question was just we were not given x values this time. There's the line, there's this parabola. We just want the region shaded in blue, and just as a first guess of what a and b. So there's just two vertical lines, and there's these sliders. I just picked the first x value to be 0.4 and the next x value to be 1, and that's clearly not correct. This region that's shaded in red is not the entire region in blue. So we should change this. Of course, we know that we had solved an equation, so we knew that starting x value should be 2 and that this ending x value over here needs to be 3. So the picture looks accurate, right? But like we got the negative 2 and 3 without relying on the graphing, right? That came last. We had, if I can remind you, kind of up here, even before setting up this integral, we just had this rough picture without any axes even drawn in of just there's a concave up parabola and there's a line that's probably going to intersect it, and we have that. And so then we need to find, for those two intersection points, we're going to need those x values because that's what's going to be right there and right there in the integral. So a very rough sketch was done, so a little bit of geometry without even the axes drawn in. We need to find what's the x here, what's the x there, so that we could finish setting up the integral, the missing pieces, and even finding those x values. It was a little bit of algebra work. We just confirmed that work with geometry. Questions on that one? Okay, I would like to ask if you would then try this next one here. If the slide would advance. So set up an integral for the area between y equals 5 minus x squared and y equals x squared minus 13. So notice again, you were not given any x values. But do a very rough sketch first. Even a sketch without axes. Okay, so this is two parabolas, right? Because it's a y equals x squared of some form. There's not like an x cubed. These are both parabolas. One is kind of upside down, one is right side up, right? So I'm actually going to use the language of concavity to discuss this. Just it's an option. There's one way to. So y equals 5 minus x squared is concave down. It's a parabola that's concave down. When you take the second derivative, you get a negative number. Y equals x squared minus 13, though, is concave up parabola. Right? When you take the second derivative, you get a positive number. So think about just how would those be shaped? You've got a concave down parabola, you've got a concave up parabola. Just draw any concave down parabola and any concave up parabola. If they intersect at all, the concave down parabola has to be the one that's above. The concave up parabola has to be below. Right? Concave down parabola, concave up parabola. There's a shaded region in the middle. Take a look. If you start in the shaded region, you move upward, you reach the concave down parabola. If you start in the shaded region but you walk downward, you reach the concave up parabola. So already the whole point is to set up that we should have the concave down parabola minus the concave up parabola. The formulas are in that order, right? The thing that we don't have here are these x values of a and b. We need to find those. So to find where these two parabolas intersect, let's set the y's equal to each other. So set equal this 5 minus x squared equal to the x squared minus 13. Either order you could write for this equation. What I did was I added x squared to both sides. I added 13 to both sides. You end up with 2x squared equals 18, and divide both sides by 2. You have x squared equals 9. Got to be careful here. Sometimes people just get x equals 3. When you square root both sides of an equation, there's always a plus or minus sign. So you have x equals plus or minus 3. That's good because we needed two x values. So the smaller x value, negative 3, will be down here. Right? So integral from negative 3 to positive 3. And then here again the order matters, right? So the parabola that's above minus the parabola that's below. Here's a picture. And I could also do that so we can see the shaded region. So you'll notice here that this x equals 3, we found, x equals negative 3 and x equals 3. We found these numbers using algebra. But like we had to get right there. That's where the integral has to stop because we don't want any more than that. Like otherwise, if you set up the integral to go beyond 3, you'll end up getting this extra little sliver of a region. You'll end up kind of getting like the shape of a fish. You got the fish body and then this tail over here. Don't want that. So we have to stop right at x equals 3 in order to truly get the region that's shaded here in purple. Okay, so yeah, there's a link to the picture if you want to click on that later. Yeah, okay. So I hope overall the big idea today isn't all that bad. I mean, we've seen certainly much worse, much more tedious things. The the key idea is I want to do one other thing with this tomorrow, though. That makes it maybe just slightly more challenging, but conceptually won't be too bad. I want to even preview the idea is that let's say the question is between x equals 2 and x equals 10, we want to find the area of the region, so between these two vertical lines, and then between the red curve and the blue curve. But the problem here is that the red curve, at least with this red curve and this blue curve, the red curve isn't the one that's always above, and the blue curve isn't the one that's always above either. Sometimes the red curve is above, sometimes the red curve is below. Sometimes the blue curve is above, sometimes the blue curve is below. But that's easy enough to fix, right? So what you do is then you say, well, this x value right here, right where that intersection occurs, that's interesting. If we just find that, then we can set up two separate integrals, right? So that's the big deal tomorrow. The graphing side of things may be a little more challenging tomorrow, but finding this x value, right? If you find that x value, then you set up for this region here, you set up an integral of x going from 2 to this number of the blue curve minus the red curve versus this other region, you set up an integral starting at this x value going up to 10 of the red function's formula minus the blue. right? So that's it in terms of big idea tomorrow. It's just the graphing sometimes gets people a little bit. Um, yeah, so tomorrow what we're really going to look at and focus on is a situation when one curve isn't always above. And then we're going to describe, at least in really vague terms, what's an application of this. So some of the days that we're losing due to the week of lost class is an application in economics, and you will not be responsible for that application in terms of quizzes or tests. But this is applied calculus, so just the last 5 minutes of class tomorrow, I just want to like preview, like cartoon version, and say you don't have to take notes on it or anything like that, but you ought to at least see it, right? Like I wanted to talk about the application without doing the skill thing, but then that would have made no sense, right? So it's like if you at least go through this process of setting up the area between curves, and then at least see the cartoon version of where this what this is good for, then in a future econ class you could set up what you need to. Um, so here's the thing, because of what this section entails, this area between curves things, I think it's very important to be familiar with the graphs of maybe those, for instance, right? Like I've got a typical exponential function 2 to the x. I've just changed the base to e, so e to the x really doesn't look morally all that different from 2 to the x. So sometimes that e gets to people. E to the x is not the same as ln of x. These are not the same. Sometimes people think these are the same. They're not the same. Right? They're not equal. They're related. They're inverses of each other, so they're diagonal flips of each other. Don't confuse 2 to the x and x to the 2. Those aren't the same. You've got an exponential here. You have a parabola there. X squared minus 9x is just a different parabola. But like I want you to be familiar with, graphing some of these. X squared minus 9 is a different parabola. 2x minus 9 is a line of slope 2 with y-intercept negative 9. So, I mean, some of the things that would be like in this list, these would be sort of typical functions that I want you to go like, oh yeah, that's what the graph of this roughly looks like, right? So it's important to have like what I would call a 5-second sketch of these in mind. It's sort of this one last piece of algebra that we haven't really used a lot, but like with this section, we end up think of like everything that you've done in an algebra class. It really appears in calculus at some point. Okay, to end class, just want to remind you, since it is Tuesday, please do the online quiz. And I would strongly suggest you start web work number 43 today.